Okay, welcome everyone to today's webinar on energy considerations and thermal desorption. I'm your host, Mike Campbell. I'm the president of RSOS Environmental located in St. John, New Brunswick. And I'm the regional sales associate for Hamers Technology in Eastern North America. Our presenter today is Jan Hamers, founder and CEO of Hamers Technologies. Jan holds 3 masters in science. He has degrees in mine engineering, geological engineering, and hydrological engineering. He also has a business degree from Solvay Business School. Jan has been working in the field of soil remediation since 1991. In 1993, Jan was a pioneer of bioremediation, soil washing, and thermal desorption at a company called Sarpi. In 1999, he started his own company dedicated to thermal treatment. In 2001, he acquired the US-based company TPS Technologies, Inc., where he began his research into new thermal technologies. His company, Hamers Technology, is now a world leader in the application of in-situ and on-site thermal desorption. Jan is the main inventor of more than 15 patented and patent-pending in-situ thermal desorption technologies. Jan lectures in soil remediation at various universities and engineering schools in Europe. He continues to be focused on bringing sustainable circular technologies to market by partnering with local companies worldwide. As mentioned, today Jan will be presenting on energy considerations and thermal desorption. In particular, I'm interested in hearing how both in-situ and ex-situ thermal desorption can reduce energy consumption below the conventional dig and haul or dig and dump approach. Please join me in welcoming Jan Hamers.
Well, thank you, Mike, and good morning or good afternoon, good evening to everyone. I'm sharing my screen here, and here is just a few of the topics I'm going to talk about were already illustrated in the title. So, but before that, just let me briefly introduce not who I am, but the company Mike and I work for, and we're, as was introduced, like a thermal desorption company, but a technology provider, not particularly a consultant or a contractor. So we develop, we invent, and we apply these technologies. We try to transfer them all over the world, wherever we can. We're based in Belgium. I'm currently talking to you out of our office in Brussels. We also have an office in the US, and you see here on the screen the people who are currently staffing it. We currently have a project working and running in southern Idaho. For those of you who might be interested in visiting it, it started 3 weeks ago and it's almost finished. I think we're going to do the sampling in the course of next week. Enough said. The topic of the day, going to talk about introduction. As I said, it's energy, and in particular in comparison with dig and dump or dig and haul, which is something I've been confronted with a lot these last couple of months and a couple of years. So yes, but why is it any better? And in particular, how much energy do you consume? So it's time to dig into it as engineers and go into the theory and then the reality, and then comparing both to get to some conclusions. So that's the topic of the webinar tonight. So let's jump into in situ versus dig and haul. What I hear a lot about it is circular economy. We have to be circular. We have to be circular economy on how we handle with waste, why we handle our lives, our energy. It's circularity. So now when we talk about remediation, how do we translate that circularity into how to deal with remediation? Well, it's pretty simple. The definition of linear economy is dig and haul. It is a primary use. We use the soil for what it was, building, construction, whatever. Then it's no longer useful. We excavate it, we haul it out, dispose of it, and we bring new soil in. It's exactly the definition of linear economy. When my shirt, I don't like my shirt anymore, or it's whatever, there's a scratch in it, so I throw it out, throw it away, send it somewhere to Africa, and then buy a new one. That's the linear economy. What we try to do with circularity is say, we have to take care of our resources, and we have to recycle as much as possible, reuse, even prevent if we could. So no, if your shirt is dirty, just clean it and put it again, or if it has a scratch, just see how you can repair it, but just don't throw it away. Now, when it comes to contaminated land, it's the same approach, but you have different levels of circularity. You could go to the first level of circularity, which is, okay, I'm still going to dig it, I'm still going to haul it, but I'm going to go to a soil treatment facility. I'm going to try to recycle the soil, to transform the soil there, a fixed facility, from contaminated soil into clean soil. I'm trying to do that in a remote place. It's called level 1. Why? Because, yeah, you have a form of circularity, but you still excavate, you still, haul it. So, but it's much better than just digging it and dumping it somewhere. Second level is, yeah, you do the same thing, but on site. You dig it, you treat it on site because it's technically easier, and then you put it back in. You don't transport it. So it's a higher level of circularity. And last but not least, the final level, or level 3, you could argue the final level is actually prevention, right? Not treating it at all, but it's treating it in situ, not excavating at all, not a single ton of soil that is excavated. So you preserve as much as possible the functions of the soil before and after. So that's essentially the highest level of circularity. That is, if you look at the comparison, dig and haul and in situ from a sustainability or environmental standpoint. So as shown here, dig and haul is essentially textbook definition of linear economy. And that's what we've been doing. And I've been doing this for 35 years now. We've been doing that for a long period of time. And why did we do it? Because it was easy, and because then it was about the only thing that was available. And there was not a lot of alternative, and definitely there was no in situ alternative that you could call as efficient as dig and haul. So that's exactly how we did it. As written here, it was easy to manage because you look at your site and your site boundaries. And if you look only at your site boundaries, it's perfect. I dig it, throw it somewhere else, bring in clean dirt. That's it, done. The problem is for the next generation. My children will take care of it. I'm done. I fixed it. Now we forget that dig and haul is one of the technologies that is known that has had the most failures, whether it's stability, whether it's nuisances, which is a lot of traffic, noise, complaints from all sides. We tend to think about it as oh yeah, it's easy, it works. It actually isn't. We accept those nuisances because we see it all over, but it's no fun to live next to a site where they have dug a lot of contaminated land or contaminated soil. And that is a topic that will come, I think, definitely more and more to the agenda in North America. It is definitely the very hot topic in land management in Europe, which is soil health, preserving the health of the soil, whether it's biodiversity, but all the functions of the soil other than just contamination. And of course, if you dig in a hole, you have a total destruction of the soil because it's out, right? You have nothing left. So that's the highest level possible of soil destruction. In situ, to the contrary, I think it's the epitome of circular economy when it comes to managing contaminated soil. Yes, it is more technical. It's not as easy to implement. It requires a little bit more of an engineer, requires a bit more time. You need to pay attention to it. But it has known over time less failures. Mostly stability is not affected. You just don't have a lot of trucks coming in and out. There's not a lot of noise. Doesn't smell. I mean, you have all those things. We have gotten used to it because we had no other choice. But once you start seeing it in situ, say, yeah, actually, much better. And when it comes to soil health, and you'll see, I'll illustrate that a little bit further in this presentation, you maintain soil health as much as possible. So to the contrary, to the dig and haul where you destroy it, when you do thermal in situ and other in situ techniques, you preserve most of the soil functions compared to the alternative. Now, that is the overall picture. Now, if we dig into the energy, here is the picture. Over 25 years, when I compiled the average energy consumption on a kilowatt hour per ton basis, this line, the blue line, is the energy consumption for thermal desorption for soil contaminated, say roughly by hydrocarbons, where target temperature is about 250 degrees. The green one is the consumption for chlorinated solvents. So typically where target temperature is below 100, say 95. And the dotted line, the yellow one, is dig and dump. When you dig 6 meters and you haul it 80 kilometers. So that's 18, 20 feet deep and say 50 miles to haul it, and then bring clean material back for 50 miles as well, but no treatment. You don't treat it, you just bring it, you put it in a landfill somewhere. As you can see, over time, the thermal industry has been pretty effective in reducing the energy consumption, pretty effective over time. And later in the presentation, I'll dig into exactly where the biggest progress has been made. When you look at the yellow line, you can see that, of course, also dig and haul has been more effective. I mean, trucks have a lower consumption now than 25 years ago. Excavators consume less as well, but still, it's not as spectacular. And today, let's say we're pretty close to one another, and now site specifics will dictate which has the lowest energy consumption. Keep in mind, on the one hand, you have clean soil, your problem is done. On the other hand, you just have sent your problem to someone else elsewhere and still have the same energy consumption. Doesn't feel like that, but it actually is. This is not something that is not with disturbance, right? Dig and haul has its own issues. Yes, it can be fast. Yes, it can be effective, but it's quite intrusive, and it has a lot of energy consumption. If you look at energy consumption, why is it? It's because the deeper you go, the lower your productivity and the higher your energy consumption per cubic meter, cubic feet, or per ton. It's been widely documented for a long period of time. And if you integrate here, I just cite one publication that compares both on other environmental impacts, and you see, these two charts here, that there is a huge difference in impact. The impact of thermal is much lower than the impact of excavation on the overall environmental quality. And then last but not least, it's a pretty, let's say, newsworthy topic, because we've been dealing with biodiversity and the issue. And I have to say myself, I always said, when you thermally treat soil, at the end of the day, you have soil that has no biological life anymore. And yeah, it's clean and it's a benefit because it wasn't before, but after that, it's dead. So that's it. You have to bring in life in it. You have to bring compost, etc., etc. And then it still keeps the structure and the texture of the soil. But that is it. I was wrong. We discovered that a little bit by accident. This is a small site in the Netherlands we cleaned 2 years ago. This is during treatment, and this is a year after. We came back on site a year after, and what we did, we did that with the university here in Leuven, where we discovered that we had more life, more bioactivity than before, and particularly more bioactivity in that area which was treated than in the next area. So and we wondered, now how come and why? Well, it seems that the reason why that biological activity is now higher than it used to be before, it's because when we cool down the site, so after treatment, you cool down and you get to an asymptote around 30, 35 degrees. By the time that energy dissipates, it takes months and months and months and months. So that's number one. You're in an environment where the temperature is pretty optimal for bioactivity. And secondly, while we have heated it, we have transformed organic matter into a form of biochar. So essentially the best possible habitat for life, or for microorganisms. So not only do you have the right habitat, you have these microorganisms that were sleeping, and then they got the best environment possible, and then now boom, they're booming. And that's what we actually saw in this project. So on soil health and biodiversity, I was really happy to be surprised with these results on our latest project in the Netherlands. That's for the broad introduction, why we believe that in situ is so important for society, for our environment, and that is definitely something we need to do over dig and dump, or dig and haul, whatever you call it. Now let's dig into the topic here about energy consumption. How do we calculate it? How do we manage it, and how do we optimize it? We start with a model, conceptual model. It is essentially a volume you need to treat. You will inject heat. That heat will be used to change the phase, to heat the volume itself, and there will be losses. That's essentially what goes on. That's the conceptual model. Now you can also put that in a formula. Not going to go into each of the terms, but it says essentially the same thing. You're going to heat your soil, you're going to heat your air, you're going to heat your water, you're going to heat your contaminant, you're going to change phase of these. That will take some energy. You're going to have energy lost at the boundaries of your treatment zone, and then you're going to have energy lost by convection. If your groundwater moves, for example, out of your target treatment zone, of course, that moves with some energy with it. So that's essentially how you put it in an equation, and then you start to take a model, and we took here a model very simple, 66 feet by 66 feet by 20 feet deep, and we consider that's a Vadro zone. We consider no groundwater just for simplicity, and our target is to reach a certain temperature where we will mobilize the contaminants. So that would typically be in the 90-95 degrees C for chlorinated solvents. It would be in the 220, 250 for hydrocarbons. It would probably be in the 350 for dioxins, PFAS, and that kind, or mercury. So it will depend on the type of contaminant. Once we reach that temperature, we know we extract the mobilized contaminant. That's the target here. What we must keep in mind is that, of course, heating the soil is completely, the amount of energy is independent of the heating technique, whether you use gas burners, we use biodiesel burners, you use electrical heaters, doesn't matter. It's an amount of kilowatt hours. It will be completely independent of the heating techniques. It will depend on soil type, mostly water content, contaminant content, of course, and then the hydrogeology. If there is a high velocity water flow or low velocity, that will impact a lot the energy calculation. So we start from a perfect world. We say we want to go from 10 degrees to 300. We're in the Vadro zone. We have typical soil 35% porosity. We have a typical density, so 1.8, 16% moisture. Very, very, let's say, common type of soil. You do all the math, as to show you, you come to 1.22 10 to the 9th joule per cubic meter. You can look at it, how many BTUs per cubic feet that makes for you guys. It's essentially 188 kilowatt hours per ton. That's, let's say, the magic number for that standard soil. My good friend and associate Hatem Sadawi has made all these calculations, and these are his assumptions based on the conventional values that are considered for the different parts of the soil. But what's more interesting is, in that case, where does that energy go? What is the use of that energy? Remember, we have no loss because we're in a theoretical perfect world. Still, 27% of that energy is used to reach 100 degrees. 55% is used to go above 100 degrees, to vaporize the water. And 17% only for, say, to go from 101 to 300 degrees. So as you can see already, water content is the key element in energy management in town. I think it is absolutely key and critical that that is known, because that will drive everything. And here the same thing for different geometries, so energy density or spacing. Those different colors just show everything is the same, but we just change the water content from 5% in the blue line to 20% in the yellow line. And you see, for the same geometry, say 2.5 meters, instead of having 55 days of heating, oops, you have 150 days of heating, right? All things being the same, it has a huge impact on time and, of course, energy. Now if we leave theory and we go to the real world, now we get to, of course, losses, inefficiencies. First, in energy production. When we produce energy, we're not always efficient. When we transfer that energy that we now have on site, that we transfer to the soil, we're not always efficient. And then once it's in the soil, it goes to the boundaries, and again, we'll see losses there. In the energy production, it's typically the conversion from primary to secondary energy. When we use electricity, for example, to heat, No, electricity doesn't come as primary energy source, so it has to be made out of something. If it's made out of fossil fuel, it's going to have anywhere between 30, in best case, is 60% efficiency. Most likely, if you work on site with generators, you'll be around 30, 32, 34%. All the rest is lost because you transform your heat or your fossil energy into heat, then into mechanical energy, and that into electricity, which then at the end will be sent back into heat. So you have all those changes in energy form, which are not efficient. So you're going to have a lot of losses there. Transfer of energy transfer efficiency to the soil. We'll talk about that at the next slide. But then the boundaries, of course, you heat something, like if I heat this room at the boundaries, there's going to be heat loss through the walls, in this case, to the sides, the bottom, on the top, and also convective loss. If my groundwater flow goes from A to B and there is heat lost with that groundwater, that's for sure going to have an impact. Let's talk about transfer efficiency to the soil. Electrical heaters, once your electricity has arrived to the site, usually with already 30, 40% efficiency at best. Now, when that turns into heat, it's pretty efficient, over 95% of efficiency. It's not the same for gas heaters or diesel heaters. Over time, I would say 15 years ago, we were at 35% efficiency. So a lot was lost. Today we're at 85%. So it tells you why you could see that big drop. It's mainly because the primary energy available on site is now transferred for almost 85% of it is transferred as heat to the soil. It used to be only 1/3. So that has been a huge step forward over time with the technology. At the boundaries, if you look at the same model, of course, you have these 6 surfaces, S1, 2, 3, 4, 5, and S0. And the loss will be a function of the temperature inside, the temperature outside. Same thing in your house. The heat loss in your house is higher if your house is very hot than if your house is cold. If your house same temperature as outside, there is no loss. So the delta T is there. And of course, the bigger the surface, the bigger the loss. So, and it's a proportion, as you say, a difference in temperature, and it's a power. And so it depends on time. So the longer your heating takes, the more losses you will have. And you can see here the amount of losses going from 0. Of course, if you can magically bring everything to temperature, you have no losses because then you reach the goal and it's done. But if it takes you, say, 2 years, you're going to spend more than actually the base energy, over 200 kilowatt hours per ton, just on losses. So it can be the biggest part of your design or your energy use could be losses by design, just at the borders. Yes, Mike, I see you.
Yeah, sorry, I had my mic off. So would you say that deeper is better in principle just because you have less losses vertically? Those losses are beneficial. Is that a safe assumption?
It's a safe assumption to say that that geometry plays a role. Of course, the total surface divided by the volume, if that's optimal, of course, you're going to have less losses. I completely agree. And then what I didn't say also is that the S0, so the surface, that is the one you can insulate, right? So
okay. So
and then there is another element on depth. The deeper is usually better because you have in situ you have a bunch of costs which are proportionate to the volume. So deeper or not, and energy is part of that, right? With the little exception you just mentioned, but mostly energy is a matter of tonnage or volume of soil. But then costs are also driven by the surface, like how many heaters do you need, right? Or installation cost, surface cost, insulation at the top. That if you have 5 meter depth or 20 meters deep, it's going to be the same cost as a surface. So deeper is better in that sense that it then makes the whole cost per ton, the installation cost, etc., lower in proportion. So yes, usually deeper is better. There is a limit. If you're below 2 meters, in situ is going to be way too expensive, and your loss will be huge compared to heating. It's perfectly fine.
thanks.
This is a good illustration of groundwater flow. So here in this case, you have an area which is I don't know if you can see my pointer here, which is this square. We heat it with a groundwater velocity from left to right, and you could see that this is a continuous flow, so it's balanced out. So you could keep that forever. This is the amount of energy, but you're actually heating a little bit outside of your zone. So if you're in steady state, you could argue, if this is the area I need to clean, I should put my heaters essentially like 5 meters to the left, and then I would heat my zone. Unfortunately, this is also theory, and the reality is often more difficult to understand and manage. But you can see here when we double the velocity of the groundwater flow, instead of having something relatively stable and under control, here you see that all your energy is just literally washed out of your site. Very important. That's one big limitation on in situ thermal when it comes to groundwater management, is the velocity. If it's too high, there are some limits. We have to take measures to control that, whether it's hydraulic measures or mechanical measures, but we can't just clean up with that kind of velocity. It makes no sense. That brings me to minimizing the losses. First thing you can do is insulate, just with your house. You want to heat your house, fine. You want to spend more or spend less on heating your house, just insulate your house, right? So that's the first thing to do. And the other part is speed energy, which is not the same analogy than with your house, because in your house, you want to reach temperature and then you want to keep it there. We don't need that. We need to reach temperature and then that's it. We can cool it down again. So it's a different approach. And that's why when you need to reach a steady state in your house and you need to keep it, we have an interest in going faster, and I'll show you why. But let's first talk about insulation. Insulation will work at the surface. We have a few cases where it's been stronger and we could insulate on the sides and on the bottoms because it was already dug out and put back in, but essentially it's at the surface. Whatever you can do, it will do. And all the rest is almost not feasible. Now, the surface, if you don't insulate, that's where you have the most losses, because that's where the delta, the difference in temperature is the biggest. So that's where if you don't insulate, it's never going to be clean on top, that's for sure. And speed, or which we also called energy density, it's same thing for your house or for your room. If you want to get to a certain temperature, say you want to reach 40 degrees because you want to be very hot, but you want to only reach this for 10 minutes, you can take your heater in your house, in your room, and put it to maximum, and then you might never reach, right? So it may take very long, but you may bring 20 heaters in your room, and it may be done in 10 minutes. That's done. But then when you look at how much energy you will have used, paradoxically, you will have used less energy with 20 heaters to reach that target than with one, because the losses of your room are a constant. And so that's why in our case, since we only need to reach a certain target temperature at a certain time and then it's done, it's beneficial to increase the energy density, so to have more heaters in the same volume. Of course, it has a cost, so like everything, it's going to be balanced by the cost of having so many heaters at some point. So to summarize that, heating time is the time required to reach a target, so it's a temperature goal, and you're going to input a certain amount of energy, and then you're going to have thermal losses. And the good image of that is a leaking bucket. So what we try to do is we try to fill that bucket, and it unfortunately has holes, which are the losses, let's say, on the sides and on the bottom. And the amount of water we put in is the energy. That's the equivalent of the energy of the heat. That's the amount of water we put in. And the losses are essentially what goes through those holes. Now, the size of the faucet matters. And maybe you can feel it better here, but if you have a very small faucet and you still have the same holes, you may never be able to fill your bucket. If you have a huge faucet, you will fill your bucket very quickly. And yes, you will use less water than with a small faucet. So smaller faucet, more water, bigger faucet, less water, more power, less energy, less power, more energy. So that's the balance we play with in thermal, because with the image of this leaking bucket, our goal is to fill the bucket and then we're done. Then of course it can empty itself, but that's the goal we try to reach. So how do we increase this? Of course, we can put more power per heating well. There is a physical limit that, of course, the soil cannot take more than a certain energy. So that's the physical limit of the soil. But beyond that, that's the only limit we have. If we are using, let's say, gas or diesel burners, if we're using electrical heaters, now we have another limit. It's the amount of electricity available. You have plenty of communities who just don't have enough energy, electricity available, and even in large cities, there isn't only that much of electricity available. So if that's your limiting power factor, you cannot put as much power as you want. Usually for gas or diesel, you don't have that limitation. They can deliver as much as you want. So more heating wells, that means higher density. Here I give you an illustration of a site where it made sense to have a 5-meter interdistance between wells versus a site where it was 1.5 meter. Now, you can guess it. This took about 30 days to clean up one batch. This took about 6 months to clean up one batch. They're much farther from each other. Makes sense. Now, why did we do this 5 meters and here 1.5? This was a 30 meters depth project. So at 30 meters, your drilling cost is huge. So now you're going to have to say, yeah, I'm going to use more energy, but that extra cost will not weigh compared to the extra cost of putting wells every 1.5 meter. That's going to cost a fortune. So case by case, you're going to have different optimization on your design. And here you can see, and this is energy density measured as distance between heating wells. If they're very close to each other, you need a lot of power. For the same case, you see you need 1.2 megawatt. And if you have a larger interdistance, you need 100 kilowatt, right? So that's sometimes if your limiting factor, the energy company or the electricity company says, I can only deliver you whatever, 250 kilowatt, that's it. You cannot go any closer than 3.25 meters. And then that means that you're going to have a lot of losses. So that is, let's say, the power limitation. So let's go and see how that translates into energy. The larger the interdistance, of course, the more losses in blue, and so the total energy cost will be. That is the difference. Remember, 188 was in theory, and now in reality, when you factor in the losses and the energy density, see how those 188 become 200 up to 450. Same case, same model. That will play. So by design, you can play on that. You can use your design to reduce your total energy. But as we'll see, and the next almost final slide is, drilling costs will play a role, equipment costs will play a role, scaling costs, of course, labor, all that will play a role in energy. So when we put that in a shaker and we put all these, then we'll get a kind of an optimal. That's the exercise we're doing for every substantial project to try to find the optimal interdistance, and it can change from one project to another. There's no silver bullet. It's no one size fits all. So I'm going to conclude here. A few takeaways. I think you could see that thermal has become much more efficient over time. Some of you have been doing that for a long time. If you remember the early days, they're gone, right? We are now in very sustainable territory when it comes to energy consumption. And remember, it's the energy consumption to make the soil clean without excavation, all included. So I think it's been a huge progress. And I think it's the merit of the whole industry of in situ thermal that has done a great job over time to work on energy. It can be influenced by proper design. Just choosing your design properly will have an impact on your consumption. So it's not just a given by God. If you use it by fossil or biofuels, of course, it's much more efficient to use the energy on site rather than to use to produce it somewhere else like you would do for electricity. And if I could beg for something, is use dig and hole or dig and dump just really as the last resort and not as the first one, which I see unfortunately, too often to say, if we can dig a hole, we do it. And only if we really cannot, we'll look at in situ. I think it's time to change that and to do something a little bit more sustainable. Voila. Thank you.
All right. I have anyone who has questions. I see there's a Q&A section, so feel free to ask questions. I have one. When you talk about chlorinated solvents, is gasoline obviously not a chlorinated solvent, but has VOCs? Does it run in the same temperature range as your? No, you still
gasoline.
Have
you will have to go above 100 degrees, so it's going to be more in the range of 200 kilowatt hours per ton than the range of 120 or something like that.
And that's for the pHs and like naphthalene and heather.
Yeah, well, some of those. If you only have gasoline, you probably have a target temperature about 180. If you have pHs, you're going to be close to 250. If you have diesel, you're going to be close to 220. But all of them are above 100.
Okay.
To us, there is a huge gap between anything that's below 100 or above 100. That makes a hell of a lot of difference, because in the one case you still have to evaporate a little bit of water, but you don't have to boil all the water out. And in the other case, you have to literally dry out everything, and that weighs quite a bit on the energy consumption and time.
Great. Another thing on excavation. I mean, one of the things that we've known, I've been in the industry a long time as well, and excavation, so often there's an uncertainty of volume. If we're going to dig it, we don't need to know the exact boundary. We'll just dig, and while we're there, we'll figure it out. And for that reason, there's scope creep. When doing in situ thermal, more likely have some certainty on your characterization. I think that's a safe assumption, but less likely to have scope creep, because you spend some time and energy defining those boundaries.
Yep, and you can also, it can happen that mistakes happen, or sometimes you can miss it. We've had cases where we could see that things were clean, and then we still could see some wells with a lot of hydrocarbons, for example, coming out at a boundary. That was a pretty good indicator that next to the target treatment zone, there was still something. And then, yeah, guess what? We went and drilled there, or the consultant in this case did, and yes, they found another source. So they would have found it with digging the hole, but you could still find it. But most of the time, yes, you spend more time because it's more technical. You spend more time upfront to identify it better, which is then also sometimes brought as an argument, say, oh yes, but we have no time to do in situ because we're in a hurry. We've been waiting 4 years and now we're in a hurry. So anyway, we know that.
Yeah. Yeah, and I think that most consultants, would really desire to understand the sites better. And I think when you're doing in situ technologies, you make a stronger case to have a better understanding.
It's a general rule. I mean, I think the general rule is every dollar you spend on site characterization is about $10 you save in remediation. That's the same rule, but
I've seen sites where that number is 100 or 1,000.
Sometimes that's the dollar you don't spend. Indeed.
Yeah. And anyone who has questions, even afterthought questions, I think they can.
Absolutely.
How would they send any questions to us?
Yep. You can send it to us. You could put it in this chat, or just send it, and of course we'll take care of that.
Okay. Excellent.
Well, thank you.
Well, thanks everybody.
Well, thanks for attending, and yeah, I think it's recorded. So anyway, see you for the next session. It's going to be in a month from now. So on a regular basis, and count you on.
Okay, thanks, Sean. Appreciate it.
Bye, Mike, and bye, everyone.
Bye now.